So this one is second and third generation HDI. So I don't, you're probably not a follower of HDI, but like I said, the first generation we've been talking about is 40 years old. So there is a second generation that's better, and there is now a third generation that's better. The third generation is only about 10 years old. And I'm not sure exactly, why these things evolve, but they do. As a step back, if you brought me in as a consultant, you want to do HDI, and you want to do it for a future product, the first thing I would tell you is do not use HDI on your new product until you've gone through these steps right here. The first step is what you're doing right here, HDI familiarization and education. Before you get into this, you should get some education. Number 2 is do a test vehicle because we need to know who your fabricator is going to be and what materials you're going to do. And everybody's HDI is always different. And so I insist that you do a test vehicle, especially for reliability and electrical tests. You don't look at HDI design rules and design a totally new product, not if you want to stay in business and keep your job. There's a lot of learning. So do a test vehicle for reliability with materials you think you can use with the fabricator. The second thing I always do is let's find your most complex multilayer and let's redesign it with HDI using the principles I've talked about. And that's what we're going to do after this session, after coffee break, is we're going to look at my clients that paid me to come in and teach them how to do HDI. And the first thing we did was a test vehicle. The second thing we did is we took their most complex multilayer and we figured out how can we simplify this and lower its cost and its performance. We redesigned. So guess what? We did not move a single component. We assumed component placement is optimal. What we did was the layers and the vias and everything like that of what we talked about the last half a day. And lo and behold, the HDI boards cost half as much, worked better, and took 4 days to design instead of 12 to 14 weeks. And so management said, whoa, this is a good deal then. The boards cost less, they work better, and they're faster to design. Right, I said, now that you kind of understand it, now go off and design HDI in the new product. Because if you have never designed HDI and you jump to it, I guarantee you're going to make so many blunders that if you'll probably lose your job, but even more, management will say, I don't want to hear anybody mention HDI ever again. It doesn't work because you didn't do your job. You jumped into something you know nothing about, and you did it all wrong, and you wonder why you got fired. So if you want to save your job, don't let your boss tell you to design the first HDI board. That's not a very safe place to be because there's just too many things that are new. Bring in a consultant that says, no, we've got to do it step by step. And the first step is reliability. Who's going to fabricate this, and is this board reliable? We've got to protect our customer. Number 2, let's test HDI design by taking this current board that's in production, not moving any parts, and seeing if we can make it faster, safer, and higher performance and lower cost. Because guess what? We can actually buy the board and run it down the production line because we didn't move any of the parts. And we can actually put it into the field. And then if all the numbers come back, then let's use it in the new design. Let's just not, cut our throat here. HDI is great, but, until you know all the secret rules and nuances and things like that, there's a lot of potholes you can step in that are really nasty. And that's why you hear people say HDI costs too much, it doesn't work, because those are the people that failed. They're not the people that succeeded. The people that succeeded aren't encouraging you at all because you might be a competitor. So they're not saying how great it is. They're just silent about the whole thing. The people that have failed say it doesn't work. The people that are succeeding, unless they're a consultant, aren't going to talk a lot about it. And why is this important? Well, because in electronics, we keep making things more and more complex. We get more pins, finer pitches, higher frequencies, rise times, more crosstalk, lower voltage. Well, and now they want you to design for the environment. They want you to design for green or design for recycle. I mean, you know, it's tough enough to do the job, but they've added a whole bunch of boundary conditions that makes it tougher and tougher. And guess what? Hey, this is going to happen the rest of your life. That's the industry that you chose. It's job security, but it means constant education and challenges. That's the fun part about it. The job's not going to go away, but it's also not going to get any easier. You know, it's just not the way. As a chemical engineer, I like to say entropy. Entropy in the universe is constantly increasing. You are the entropy of electronics. It's constantly going to get more complicated for you. Nothing I can do about it. It's just the rules of physics, of the cosmos, is that it's going to get tougher for you. You know, if you meet the challenge, you're going to get more money, be more profitable. And the other ones are going to go into marketing and sales because it's just too much work to keep up. You know, or management. You know, in management, you can then not learn anything at all and just stay there and float the rest of your career. But if you're going to be a technologist and a board designer, it's going to get more fun and more exciting and more challenging. One of the things is about density. Right now, we're over here in 10 to the 2 and 10 to the 3 connections per square centimeter. We are heading towards 1 million connections per square centimeter over time. Guys, when I mean that it's going to get tough, I won't be around. I'll be dead, but you'll still be working. And you're going to go to this round and to this round and this round. It's going to get a lot more fun. And people are going to make a lot of money that figure out why you would do this. Don't ask me why you would do it, but there's a reason sooner or later. And so we already have moved beyond HDI. Have you heard of the term SLP? Well, HDI is now an old term, 40 years old. The new term that Apple uses is SLP, semiconductor-like printed circuits. And the reason it is that these printed circuits are more like silicon devices than they are printed circuit devices. So HDI is definitely a printed circuit. SLP, well, it's organic, but it looks more like a semiconductor than it does a printed circuit. Only AT&S is invested in SLP in Europe. We have 3 in the United States, and a lot are going on in Japan and Taiwan. But the new term is SLP, so look for that term, because that term is higher performance, higher density than HDI is, because it's quote, more semiconductor-like. So one of the things is we're switching to a better material, and that's glass. We're making our circuit boards out of pure glass, because glass is cheap, it has a terrific dielectric constant, and it's very smooth, so we can do 5-micron geometry. Not film, you know, not glass weave, pure glass. And so I've made a lot of circuit boards out of glass, because my last job, our company processes 500,000 square meters of glass a year with ITO sputtering. So we do 500,000 square meters of ITO, indium tin oxide sputtered glass. And with that, I made all of our circuit boards out of that glass. But I'm using 5 and 10 micron geometries instead of 100 micron geometries. And they work great, and they're really cheap, and they're thing. And so glass is coming. So you don't want to let people drop circuit boards anymore because they're made of glass. And they don't bounce. They shatter. So we are changing the fundamental materials too. That changed. The other thing is that we keep adding buildup layers. So we went 2 plus N, then 3 plus N, and then 4 plus N, and eventually went to ELIC, which is any layer interconnects. So after we did 4 buildup layers that are stacked, we stopped using that and started going to stubless routing, which is ELIC over here. And so you can see right there, this is SLP. And so the iPhone 10 and the iPhone 11 are SLP. They are not HDI boards. They are true SLP boards. So if you go to the Google and do a breakdown of an iPhone 11, take a look at the circuit boards and the geometries there, and you'll say, I've never seen a circuit board like that before. Yeah, it's SLP. But now everybody is starting to talk SLP. So it's going to start to show up in whatever venue you're in. I don't know when or why, but it will show up. So, a 2 plus 8 plus 2 for this is a GPS navigator in a BMW. No, okay. They notice they stack the vias on top of drilled vias in the core. 3 plus 4 plus 3 is a smartphone kind of thing. A 4 plus 6 plus 4, this thing is a notebook computer, small notebook computer system. A ELIC, this is a part of a Samsung phone. It's the ELIC structure. And so here, so the ELIC materials in terms of listing the different materials and the stacking and some of the design rules that go on, including flex rigid. So they can be flex rigid with the HDI on ends of them, and things like that. We're getting into all kinds of permutations and combinations of these things, including, rigid structure in which the poly image does not go into the rigid part, but it's sitting next to it. So here's a map of all the different HDI technologies from generation 1 to generation 3. And they're listed by color codes and numerical ones. And if it looks complicated, it is, because you notice that forming the interstitial via hole, IVF, we have lasers, we have photo image, we have screen printing, photolithography, and placing components in lasers. We have different ways of making the hole, not just the laser. There's, I don't ever heard of photodielectrics? So we have dielectric that is photosensitive, and so all we have to do is expose it to ultraviolet light to make a hole. We don't have to use a laser. So that's second generation. They got rid of the laser on the second generation. You ever seen, well, I'll show you screen printing, but so, and metallizing the microvias, we got electroplated copper, conductive paste, bump connection, sheet coppers, and so we have different ways of metallizing what we just did. And then the product name is on the right-hand side up there. They go from 1 to 14. Number 1 is what we build in North America and Europe. So North America and Europe build only one of 14 different kinds of SLPs and HDIs. So if you want, well, what are the other 13 used for? Well, that's what we're going to spend a little time talking to you about what your competitor is doing that you've never heard about. And the competitor is Asian, especially Japanese. These are all Japanese inventions. The Chinese just copy whatever's running around. They don't have anything, but the Japanese are pretty innovative. And you know, I've been talking about the #1 yellow all day long. And the Japanese said, oh, we're going to do better than the Americans. So they came up with 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. They didn't come up with 14. 14 came up with this wild American named Joe Felstad. I don't know if you've ever heard the name, but he has 200 patents and is always coming up with a crazy idea that's pretty good. But number 14 is a technology that Joe came up with that we call Occam. And you notice it has its own separate line because it's so bizarre that it doesn't match any of the other HDIs. But the other 12 are Japanese. And everybody in the world licensed from the Japanese. The foremost of them is a company called Ibiden in Japan, the kind of grandfather of making these packages. And so this HDI technology kind of looks like what we've been talking about all day. They got FR4 prepreg, they've got copper foil, and they got copper-plated vias. But the manufacturing process, though, is from the ground up, you know, not from the way we do it, laminate into a core. So they build up with a single-sided copper-clad material, and they laser drill through the dielectric to the copper, and then they build up. One of the reasons you do this is so the vias are all under the pad. The vias are not in the pad, the vias are under the pad. And when the vias are under the pad, you can do landless or very small vias, so it's very good for miniaturization. And this is a process, again, the Japanese use, and Ibiden in particular uses. The FACT EV is one of the most popular in Japan, and it's popular because the metallization, they start with material that has no copper on it, and they do the semi-additive process, SAP, and build up from that. And they use a liquid dielectric. The advantage of a liquid dielectric is it's much lower cost, and you have infinite thickness variation. So you can perfectly match impedances to your line width because you don't have to buy laminate cores. You use a liquid coating and then cure it, make it any thickness you want to match the impedance level without wasting material, kind of thing. So a FACT EV manufacturing process starts with a double-sided copper clad, because that's the power distribution layers. And then they build up the dielectric and then electroplate the vias, but then use a liquid dielectric. Now, one of the reasons they use a liquid dielectric is so they can use liquid crystal polymer, LCP. LCP is a terrific low-loss material. And it's one of the secrets of how you get to 5G is to use a liquid crystal polymer because it's got 0.00018 dielectric loss. So it's as good as Teflon without being as tough to work with as Teflon is, and it's a liquid. So you roller coat it or flow coat it or spin it onto your dielectric as per the semiconductor, and then cure it, and then you metallize it. And you have a way of precisely controlling the dielectric properties and thicknesses. And so it's called FACT EV. Then there's solid interstitial vias. This is part of the 2.5 to 3rd generation. What they did is they got rid of electroplating because of the environmental green aspect. And they went to making vias out of paste. Now, the nice thing about making a via out of a paste is that you can ignore aspect ratio. So you want a 30-to-1 aspect ratio? You physically force the paste into a laser drilled hole until you have a 30-to-1 aspect ratio. Nobody can electroplate that. But they can make the board because they're not using liquids, they're using a paste. And and it has a hell of a lot of these. The two best are American, though. The other ones are, and the two best I consider are Ormet up there. That's a company in San Diego, and Paralec over here. And the reason I consider them the best is that their paste is a transient liquid phase sintering metal. Kind of get that? Transient liquid phase sintered metal. So their paste is kind of like a solder paste, but it's not solder. It's copper, tin, and bismuth in a paste, in a binder. And you screen print it like you would a solder paste for assembly, but you're screen printing it into a via hole that either drilled or laser drilled. And you screen print it until it's all filled up, usually with a vacuum chuck so there's no air. Then you dry it, and then you sinter it. And at the sintering temperature, the binder is driven off, the liquid melt, they connect to the lands and the other things, and they form a solid metal via. All the rest of these are metal particles in a dielectric. So the Daikin, or the Panasonic AltiumLive, or Toshiba, or Namix, or Tesla, North Corporation, or Denso, or Shinko, or Victor, those all use conductive paste, and so it's either silver or copper particles, very nano dimension, in epoxy or some thermal set resin, and those are forced into the via, and then the metal particles touch each other to provide the conductivity. But again, there's no electroplating. And the reason is the electroplating is the big waste generation and water contamination system. So these ones get rid of the whole environmental issue about those things, but they also make it simpler to manufacture. The most famous, one of the most famous is the OrmaLink. And the OrmaLink is this transient liquid phase sintering. So what you're looking at is 4 mil pads, well, 100 micron pads, 20 micron vias. This was manufactured 25 years ago. So this was high yield, high production, but this is 25 years old. So hopefully you've seen this before. If you haven't seen it before, you're not reading enough. Because this is it still runs today, and the company is still there. But most of it's been used by IBM. So IBM used it to make 60-layer boards out of Teflon and things like that. So the blue streak and all these massive big IBM machines, they're made out of 8 and 10-layer multilayers that are sintered together to be 60 layers. They're not made as 60 layers, they're made as 10-layer, and they use this transient liquid phase to sinter all the stack up to a total of 60 layers. That's how IBM does it. So again, these cross sections are 25 years old. I mean, and the reason is they still blow you away today, but they're still nonetheless 25 years old. This is what they were doing 25 years ago with IBM, including these are inner layers where they don't drill and plate them. It costs a lot less if you kind of laser drill and fill them with a paste to do your buried via connections. And this is the OrmaLink process. One of the things is that the OrmaLink can do polyimide film layer pairs. And so what we have up here is 3 double-sided flex circuits. And then these are the bonding sheets. And this whole thing is bonded together with the OrmaLink to form a rigid PC board made out of totally separate flex circuits. So if you want, part of this can still remain flexible. So it's really innovative, even though it's 25 years old. They used to make some of this stuff about 30 kilometers from where I used to live in Colorado. It's pretty interesting because we had a plant there that would do roll-to-roll polyimide, and they use excimer laser to drill 25 micron holes about 20,000 per second. And it costs the US public and the military about $100 million US for this state-of-the-art factory to make all of these circuits. And it was interesting because the vacuum sputtering, to make something stick to polyimide, they would laser drill the holes. Then they would put them in this 2-story vacuum chamber and sputter titanium on them. And then the next vacuum chamber would sputter copper on them. We put down about 1,000 angstroms of titanium and about 3,000 angstroms of copper, put off, and then we would go through electroplating up to 5 micron kind of thing. And the 2-story vacuum tower were Soviet Typhoon class submarines that the Finns had pulled off the bottom of the Baltic and sliced up and welded flanges on it and sold to us as vacuum chambers, titanium vacuum chambers. But they were actually declassified, sunken Soviet Typhoon missile submarines. So they were doing a great business stealing Russian submarines off the bottom of the Baltic and turning them into huge vacuum chambers on big railroad ties. You'd set all this stuff up, and then the railroad ties would bring these two things together, and we'd pull a vacuum and start the sputtering process, but it was 2 stories tall kind of thing. And I always used to wonder, because visiting there, when I walked in there, they handed me a radiation badge. When I left, they took the radiation badge back. And it always bothers me if somebody hands me a radiation badge. And I asked why. They said, well, these Russian submarines, they're still radioactive, highly radioactive, the Russian subs are. I said, well, what about the sailors? Well, Russian sailors die young if they're on a Typhoon-class Soviet submarine. Well, I said, don't the Russians mind if you steal their submarines? Well, they don't know we've stolen it. And because first thing we do is we slice it up into these oval-shaped things that turn out to be vacuum chambers. The only way you would know is Russian is that it's still radioactive. I thought, oh, that's a good business. The Finns are smart. The one that you may read about is Panasonic's AltiumLive. This probably has more publication than anything else. And AltiumLive is famous because AltiumLive uses the conductive copper particles in the epoxy. But the one thing about AltiumLive, this is not FR4. This is Thermount. Anybody here remember Thermount? Oh, okay. Well, Thermount is a polyimide paper. Get it? You know what I mean? Okay. So you take Kevlar that you make bulletproof breasts, and Kevlar is filaments. You chop the filaments up, and you put them into a paper making machine, and you draw this out as a paper, but it's a thermoplastic paper made of Kevlar. Okay? The nice thing about this, it has the same coefficient of thermal expansion as silicon. Okay? The only thing you got to worry about is that it's somewhat bulletproof because it's made out of Kevlar. So it's really, really tough to mechanically drill, but it laser drills beautifully. So you don't want to mechanically drill it because you get a couple hundred hits and have to change the drill bit because you're going through Kevlar in it. But it's a Kevlar paper. The beauty is it's extremely smooth, and the coefficient of expansion is just fantastic. And you've never heard of Thermount? No, some of you got to have heard of Thermount other than Pete. Come on now. You can't tell me you're in the printed circuit business, you've never heard of Thermount? How many people have had a materials course in the last 10 years? Oh, nobody raised their hand. Okay. You must invest in a materials course. It'll take 1 to 2 days. You're woefully ignorant of the latest materials for printed circuit. If you don't know what thermount is, you failed my test. Come on, because it is a key HDI material. Because number one, it has fantastic dielectric constants. It's very thin, and it's very robust, and its XY coefficient is matched to silicon, which is great. But anyway, AltiumLive is made out of this thermount paper, not FR4. And it's a great material. They make it in Japan. So, you know, we can go in, but again, they start with the thermount as a prepreg, and they laser drill it. They put the paste in it, and then they put copper foil on top of it, and then they put it in a lamination press and cure the B stage epoxy to C stage. So now they come out with a rigid material that already have all the vias connected. And now they do is they image the outside, and the vias are under the pads, because so they don't have, they don't have to now drill and register, because they drilled the base material. And the base material will drill 10 to 100 times faster than FR4 will drill because of the glass. So there's some real advantage in this manufacturing process. But they build layer pairs. So they build a whole bunch of 2-layer boards, electrically test them, and the very last step is they glue them all together into a multi-layer that you see up there. The advantage of this is if they find electrical failures, they throw that layer pair away and substitute a new one. So they don't have the yield loss that we have in North America and Europe here, where we're going to do a 4 buildup, and on the last buildup we make a mistake and throw something very, very expensive away. They build all the layer pairs independent, test them independently, and have only one lamination at the very last step. So there's a cost advantage of this. And you will find these multi-layers being quoted much cheaper than the multi-layers you're getting from your current vendor. That's the problem, is that when the Japanese come in and start offering this, they're offering prices that nobody in Europe can match. And they're good boards. So be forewarned, there's a bunch of Japanese technology that can save you a lot of money and give you advantages if you do. And typically it's done by CMK. CMK is the one that came into North America and killed us on prices. So everybody had to lower their HDI prices to compete with CMK. Because CMK is using a newer technology that's simpler with higher yield than our HDI technology. That's progress. I don't know if CMK is here in Europe, but the Taiwanese have licensed it, and Unimicron over here in Germany wants to put it out. So you got a shark sitting in your water ready to pounce on you from Unimicron over here, very close to Frankfurt here. And they've licensed this technology. AltiumLive has a fine pitch one for 0.3 millimeter, 0.4 millimeter, 0.5 millimeter. So they use their old technology for the core, and then they have a buildup that's even finer pitch, made out of polyimide film. And the polyimide, again, so the outside is polyimide, the rest of it is kind of epoxy. Not fiberglass, but epoxy. And VIN, Victor Interconnect Technology, again, uses laser drilling. It uses FR4 prepreg, and it uses conductive paste, either the silver or the copper type of conductive paste. Same with MSF from Shinko, but they use resin-coated copper, RCC, no glass in theirs, conductive paste, and laser drilling for the vias. And so both MSF and VIL start with the prepreg laser drill, fill it, put on the copper foil, laminate the prepreg into a core, and then start imaging the outside, and then electrically testing it. And when we got all these layer pairs, put them from one final lamination where the whole stack is put together. The same thing called PALUP, which is pattern prepreg layup process. The big difference with PALUP is the first one to make thermoplastic successful. So they have a green material that can be recycled. So that's a wave of the future, that printed circuit boards, instead of going to landfills, when you're through with them, we grind them up and make more printed circuit boards out of them, because the dielectric is thermoplastic, not a thermoset. And we can reuse the thermoplastic. It's recyclable, and it's a green. The Japanese were the first to kind of develop a recyclable green printed circuit board technology. But there is a wave of the future there. And PEEK seems to be a pretty good thermoplastic dielectric. So this is how a PALUP board is made. It's made quite a bit different than a conventional PC board. But uses a laser and uses a paste. So they don't have electroplating. They have a recyclable material where there's no waste. Anything you don't use, you grind up and re-extrude as a plastic sheet. You know. So the costs go down because you don't waste as much material. You don't throw things away. And you don't have wastewater treatment. And then the last one is a thing we call buried bump interconnect technology developed by Toshiba, which is now owned by the Taiwanese. So the Taiwanese own this. Foxconn owns this because Foxconn bought Toshiba. And this one is kind of bizarre. On this one, you take a copper foil and you screen print a silver paste on the copper foil for the vias. You cure them so the vias form a little kind of thumbtack. You put prepreg on top of this in copper foil, and you put it in a multi-layer press, and the silver pushes its way through the prepreg to the other copper side and bonds to it and forms the solid metal via. But there's no laser. You just screen print this pattern on here. So 4 different companies in Taiwan have licensed this, and about 6 from China have licensed this Japanese technology. It's quite a bit less expensive than the conventional HDI. I don't know about its reliability, because I personally never ever got a hold of it or did any testing of them. But they also have a fine pitch. So they will go down to 0.2 millimeter pitch, 0.3 millimeter pitch, 0.35, 0.4 millimeter, 0.5 millimeter. So when you start getting down to these new really, really tiny chips, even with a laser, it gets tougher and tougher to figure out how to design the PC board. Well, the Japanese already have that SLP or HDI technology for those new generation of chips that are very, very fine pitch kind of thing. The last one is called Neo-Manhattan bump, NMBI. And Neo-Manhattan is interesting because, again, they don't use a laser. What they do is they sell you a solid copper sheet made out of 2 different kinds of copper. And one side of the copper you image and chemically etch to form the vias. The other side of the copper is going to be your traces and lands. And they use a liquid dielectric like LCP. So this thing is, they start with this base copper material that are 2 different kinds of copper. And first they image and etch the vias. Then they apply the dielectric liquid, cure it, and then attach the copper foil to the other side. And then they image it and form a layer pair. And then these layer pairs are tested and then stacked up to the final one. But again, they don't use a laser, and the copper is already there. You're taking the copper away. You're not adding any copper. And there's much lower ohmic, because this is not a paste. This is a solid copper via. So there's a lot of advantage of doing it that way. The thing that I think is fun about them is that they're a 3rd generation HDI, and they're competing with a second generation. So they talk about their landless vias, how much better they are than vias with lands. So one of the things is their stuff is 100% landless and much more reliable than vias with lands. So I thought an interesting juxtaposition that this new generation of HDI, because they're landless, they're higher reliability than the second generation that has lands on their vias. But to me, that's kind of funny. You see, trace just kind of drops into a hole, landless. That's kind of a humorous juxtaposition. So, but unfortunately, no HDI material is perfect. At least we haven't found one yet. There are always advantages and disadvantages in cost. We're perpetually going after. If you actually look at the market, this is what people today are using. And guess what? Only 20% of HDI boards are made out of conventional prepreg. 80% is made out of either resin-coated copper or what we call laser drillable prepreg. And laser drillable prepreg is also called spread glass. And it's much, much thinner than conventional prepreg, but also there's no glass resin knuckles. The dielectric constant is uniform rather than being separate to get away from the skew effect of dielectric constant changing at a high speed because it hits the glass knuckle and reflects, hits a resin thing, where the conventional FR4 is simply not suitable for HDI because the glass weave is the dielectric constant changes. The laser drillable, I have pictures of it, is they've spread it out so the dielectric constant is totally uniform no matter where you put the via. You don't hit resin-rich or glass-rich areas. There's also a new material called Zeta Cap. And Zeta Cap is an HDI material in which there's copper foil, polyimide resin, epoxy B stage. So it's a resin-coated copper, but the first layer is polyimide. And so this eliminates, with lead-free assembly, cracking, the whole cracking problem you have with lead-free and FR4. Because one of the problems with FR4, if you're not doing anything right, if you drop a lead-free board, half of the BGAs will pop off. I don't know if you know that, and that's because the current FR4 laminates are not very good because to get the higher temperature, they add phenolic. When they added phenolic, they made the resin brittle. And so now you can crack, your BGAs can crack off the board. And this happens all the time, but we mainly keep it a secret from you that we've got big reliability problems with our new FR4 materials only because of lead-free. When we had tin lead, we had dicide-based systems that were kind of rubbery, which was great. When we had to go to higher reflow temperatures, we had to go to a higher temperature thermoset, which is pretty rigid, and that we call cracking. Well, one of the solutions is this material where the copper is attached to a polyimide layer that has a higher temperature resistance than the epoxy layer. So Zeta Cap improves thermal performance for fine pitch BGAs, especially if you're encountering cracking in your board design. And the last material is ABF. And ABF is how we do super fine line, because this is a thermal set film that we can do, 20 micron, 10 micron, 5 micron lines and spaces on that we can't do off a laminate. And this comes in what? 2, 4, 6, 8. This comes in 10 different materials of different resins for different applications. But the other advantage is that whereas a normal multilayer sits in a multilayer place 60 minutes to 2 hours, this laminates in 6 minutes. So using this material, you have about 20 times the productivity that you have in North America or Europe. So the way your fabricators are doing it, this technique is 20 times faster, which means you can push a lot more through with finer lines than, because the technique you're using is 60 years old. We haven't changed lamination in 60 years. This is only about 5 years old. And it's called ABF because the company that developed it, Ajinomoto, their only other product is monosodium glutamate, accent, the flavor enhancer. So they have a food product, glutamic acid, and they have PC board material. It's a strange, set of products. But already the Taiwanese have developed a duplicate, and DuPont has developed. So there's soon to be a DuPont and a Taiwanese equivalent other than the Japanese ABF. I won't go into all the details, but they're very cost effective and a superior technology the Japanese have developed to what we use today with these conveyorized vacuum lamination machines that are conveyorized. So you don't stick them all into a press and then press them for 2 hours. They just move along the conveyor and are vacuum laminated up. The details of how the vacuum lamination step works along the conveyor. And remember, this material has no copper on it. So all of the metallization is what we call semi-additive, SAP, process. And this is some things about how you do the permanganate etching for adhesion promotion for that metal layer. But you can see, 16 micron lines and spaces, 10 micron lines and spaces. Right now, my friends in Asia are doing 5 micron lines and spaces with this material and making about 100 million of these a year. All of you own it because all of the Apple and other use these as packages. So the chip goes on these guys, and these guys get soldered onto the PC board. So the good news is all of you own this technology. You just didn't know that you had bought it in the smartphones. And that the geometry in your smartphone is 10 micron and heading down to 5 micron. And so that's where the SLP comes from. Semiconductor-like processes is talking about this technology that is really semiconductor geometry, but it's still a printed circuit. So it's a semiconductor-like printed circuit. And that means it's more exotic and higher density than HDI, high-density interconnect is. We added a whole new term in there. And this is a little bit about material we've developed that we're keeping secret from everybody in the world, things like Vialux. So we do have epoxy-based dielectric films that are being kept secret, but I don't know why. This one, I think, is McDermott, Alpha McDermott. So they have a great material, and they're keeping it secret. Some of the other ones are Oak Mitsui has a copper foil for 5G that is mirror smooth. And the reason is the copper losses in 5G versus the dielectric losses. You can't have copper that looks like this on the back side because your copper losses at those frequencies goes up astronomically. So instead, the copper has to be mirror smooth. And what we do is we glue the copper to the dielectric using nanotechnology. So we actually have these nanotechnology glues that glues this mirror foil to the dielectric with pretty good peel strength rather than mechanically abrading it like over here. And that's because the 5G, we got to worry about dielectric losses and copper losses. And we can't afford on skin effect to have one side of the copper rough because then our losses go up. And so that's where we come up with semi-additive, we call SAP. The semi-additive is because we're using more and more dielectrics that have no copper on them, and we've got to add the copper to them. So we have multiple generations of semi-additive. And this is kind of what some of these semi-additive processes look like for advanced buildup. Let me move over here to MSAP, AMSAP, SASAP in terms of panel sizes. You can start looking at all these things are in semiconductor geometries, but these are real materials. This is from Atotech over in Nuremberg that sells this around the world. And the reason this is important, when we get to it, is there, Apple and Samsung. So this is the iPhone 4S, the iPhone 6, the iPhone 7, the iPhone 8, and the iPhone 10. The blue is the battery. The one around it is the circuit board. And down below it is the phone thickness, the phone area, the circuit area, layer count, the lines and spaces. So the 4S was 10 layer, 60 micron geometry. The 6S was 10 layer, 55 micron. Phone 7 was 50 micron, 10 layer. The 8 was 30 micron, 10 layer. The 10 is 30 micron, 8 and 10 layer. And the 11 is 10 layer, 25 micron. You know, in case you want to know what's inside your iPhone, well, that's, and interesting, and look how big the battery's got over time. The battery keeps growing on this. And there's a side view of the SLP making up the iPhone 7 and the iPhone 10. We don't have any pictures of the iPhone 11 yet. But that is really a complex circuit board geometry. Good, 25 micron lines and spaces. That's even the iPhone 7 was complex. The Samsung looks the same. There's essentially no difference. Because you can see, look how many vias they stacked on this thing. Whoa, these are. I haven't got the slightest idea how long this stuff lasts in terms of reliability. You know, I know who makes them, who assembles them, but you know, they'll probably last long enough that you'll sell it, break it, lose it, you know, and get another one before the iPhone 12 comes out, or the iPhone 13, or the iPhone 14, or whatever it is. The nice thing about the iPhone 10 and iPhone 11, they are not 5G compatible. The reason is because nobody really has 5G networks. And by the time we actually have a 5G network, the iPhone will be 5G compatible. But there's no point in making an iPhone 5G because it's not going to change the performance without the networks out there. So people criticize them for not having 5G. What can you do with 5G? 5G is for factories and for cars. It's not for mobile phones, kind of thing. With that, we get a coffee break.